Awesome. Can everyone hear me? Okay, great. So thank you all for coming. I'm Shivam. I'm going to be talking about the Pauli spectrum of QSE0. This is joint work with Natalie, Fran, and Henry. Natalie was supposed to give this talk, but she got food poisoning, so I'm here in her stead. Awesome. She's okay. She's doing fine. So this is a talk about quantum circuit complexity. Unsurprisingly, sorry, the clicker is not working. Um, Sorry about that. If it's easy, I can stand. I can just use the laptop directly. Okay, so in the meanwhile, here's maybe an entertaining story. Natalie was supposed to give the talk. She got food poisoning, but then Fran was supposed to give the talk. She lost her voice, and I guess technical issues, but no more technical issues. Yeah. Um, Thanks. Okay, great. So the Q, unsurprisingly, stands for quantum. And when we think of quantum computers, we think of these expensive devices sitting inside massive refrigerators. And we think of New York Times articles claiming quantum breakthroughs. But all of this is rooted in complexity theory, right? Like we started thinking about quantum computers because um, quantum computation was an extension of the classical notion of efficient computation. So all of this is in some sense rooted in complexity theory. And today, quantum complexity theory is like a rich and broad field with connections to a bunch of different areas, deep ties to mathematics, physics, and even classical complexity theory. But today in particular, I'm going to be talking about quantum circuit complexity. So it's a concrete and simple model of quantum computation. And this area of quantum circuit complexity is connected to all of these other strands, but I'm not going to focus on any of these connections. I'm just going to focus on quantum circuits for their own sake, right? So the quantum circuit model is something I'm guessing all of you are familiar with. It's a really, this is the standard quantum circuit model. You've got a bunch of input qubits. You measure the output, and you have single and multi-qubit gates. The depth of the circuit is the number of layers of gates that you have, and the size of the circuit is just the number of multi-input gates. So single input gates do not count towards the size of the circuit. And this is the standard circuit model. We want to, and for the past 20, 30 years, we've been trying to figure out what these circuits are capable of computing. So we've designed some algorithms. We've gotten some understanding of this. But the focus on this talk, or the focus of this talk, is going to be on what these circuits cannot compute. So we want to try to find explicit problems and explicit tasks which are hard for circuits. Or in other words, we want lower bounds on the size of circuits for certain computational problems. Okay, and the only way, in some sense, that we know how to reason about this in order to show lower bounds is the so-called light cone argument. And this is the following really simple insight. Let's pretend that all your multi-qubit gates in the circuit are 2-qubit gates. They only act on 2 qubits. The light cone argument just relies on the following simple fact that if you have a depth D circuit, and you want to focus on some output qubit, then the number of input qubits that influence the output, that single output qubit, is at most 2 to the d, because each multi-qubit gate only acts on 2 qubits at a time. So this is a really simple argument, and in some sense, this at least to us felt like this was the only trick we had to analyze these kinds of circuits. And so the question that we started with when we started this project was, whether we can actually go beyond light cone arguments, right? So the light cone argument only works when the gates are local, when they're acting on like 2 or 3 or like some bounded number of qubits, and it's behind all known quantum circuit lower bounds. And we, in order to get some inspiration, we actually turn to the classical setting. So classical complexity theorists have been proving circuit lower bounds for like roughly 60 years, and there's a lot of stuff out there, and so we look to the classical setting for inspiration. So in the classical picture, it's the same goal. You want to show strong lower bounds on the size of circuits, computing some explicit Boolean function, some explicit function. And the holy grail of classical circuit complexity is to prove lower bounds for polynomial size and or not circuits, or P over Pauli. But we've failed spectacularly at this, or there's not been much progress on this problem. And so we turn our attention to restricted subclasses of the circuit complexity class, right? And we've had a lot of success over here. There's been, we have a really good understanding of certain subclasses of P over Pauli. And in particular, one class that is really well understood is the circuit complexity class AC0. So I'm going to quickly tell you what AC0 is. It consists of gates which are and or not, and or gates. You can assume that all the inputs have copies of the negated variables as well. And you alternate between the layers of ands and ors. The number of layers you have is the depth of the circuit, and the number of gates you have is the size of the circuit. And the 0 in the superscript just means that the depth of the circuit is a constant. So for the rest of this talk, think of 100 or 110 layers of ands and or gates. Okay. And we have a host of classical techniques to prove lower bounds against these kinds of circuits. So this is some really, really nice work back in the 80s and 90s, which allows you to prove circuit lower bounds, such as switching lemmas, the polynomial method, and Fourier analysis. And a lot of these classical techniques also have very recent and very modern applications in seemingly unrelated areas. So like these techniques which were developed to prove circuit lower bounds have found applications in learning theory, algorithm design, and even pseudo-randomness. And so it's natural to ask if you can lift any of these techniques to the quantum setting, to the setting of quantum circuits, right? And it wasn't clear to us how to analogize the switching lemma or the polynomial method. There's a very natural way to do Fourier analysis for quantum circuits. So that's going to be the focus for the rest of this talk, right? And I'm going to start by telling you how Fourier analysis works in the classical setting to prove circuit lower bounds. It's going to be kind of a cartoon sketch. And then I'll tell you what we do with quantum circuits. Okay, so Fourier analysis of Boolean functions is a super rich, super well-studied field with lots of connections, lots of applications. These are two really nice monographs on the subject. But the key insight is to express Boolean functions as polynomials. Okay, so I'm going to switch from treating Boolean functions as things that take in 0, 1 bit strings and output 0 or 1 to things that take in plus or minus 1 bit strings and output plus or minus 1. And this might be the most mathy slide, so I apologize, but as a concrete example before the math shows up, if you take the parity function, which takes in n0, 1 bits and outputs 1 if and only if the number of 1 inputs is odd, in this new notation, it's just the product of all the input bits, okay? But the so-called Fourier transform of a Boolean function is this really easy fact, which says that every Boolean function can be written as a multilinear polynomial. So the things in the parentheticals are just monomials, and there's a hand. Okay. And so this is just a way to write a Boolean function as a polynomial. And this thing's called the Fourier expansion of the function f. It's just a Fourier transform onto the space of monomials. And these f hats, which are indexed by subsets of n, are real numbers. They're just the coefficients of these monomials. Okay. And well, you might ask why you care about these, why you might want to do the Fourier transform. And kind of the general idea here is that structural properties of the function of Boolean functions, especially complexity theoretic properties, get encoded in these Fourier coefficients, and we'll see an example of this in just a slide. Okay, so we've got the Fourier transform in hand. So let's go back to AC0 circuits. This is the picture that hopefully we all have in mind, and you can ask what the Fourier spectrum of AC0 circuits looks like. Okay, and in the 90s, there was a lot of work on the Fourier spectrum of like restricted classes of Boolean functions. And Lineal, Mansour, and Nissan in 93 proved the following bound. They showed that if you have a depth D size S circuit, then the Fourier coefficients have the following tail bound kind of behavior. Okay, so let's make this concrete. Let's pretend that the depth is 100 and that the size is polynomial in n. All they're saying is that the contribution to the Fourier expansion from the monomials of high degree, degree at least k, is inverse exponential in k. Okay, and the main takeaway, if you want a one-line summary of the result, is that AC0 circuits are well approximated by low-degree polynomials. Okay, and so let's see how we can use this to get circuit lower bounds. So let's plot the Fourier spectrum as follows. X-axis is going to be the degree of the monomials. Y-axis is going to be the weight, the L2 weight at level k, or in other words, sum of the squares of these Fourier coefficients of the degree k monomials. That was a mouthful, but hopefully it makes sense. And so for the parity function, which we saw a few slides ago, all of its Fourier spectrum sits at degree n. It's just the product of all input bits. So it's a degree n monomial. That's the whole function. And what Lineal, Mansour, and Nissan showed is that AC0 circuits have a spectrum that looks like this. Right? It has some kind of tail decay in K. Great. So this immediately implies that AC0 circuits cannot compute parity. But because they did, because of some nice properties of the Fourier transform, it's not too difficult to show that not only does AC0 not compute parity, it in fact correlates super poorly with parity as well. Right? So they showed that any AC0 circuit has half plus inverse exponentially small probability of being right when computing the parity function. So just to put this in context, if you take the depth 0 AC0 circuit, which outputs the constant 1 function, you will be correct on parity for half the inputs. And this is saying that if you've got constant depth, you only gain inverse exponentially small advantage. Okay? So this is this is a really nice result, and they get another consequence, which I hinted at on the previous slide, namely that because AC0 circuits are well approximated by low-degree polynomials, if you want to learn these circuits, if you want to learn these Boolean functions, you just have to estimate the low-degree coefficients of the Fourier transform. So this gives you a really simple algorithm to learn AC0 circuits as well, right? So just to summarize what we know about AC0 circuits, we know a lot more, but this is what Lineal, Mansour, and Nissan showed in 93. These circuits are Fourier concentrated. We have correlation bounds for the parity function, majority function, any high degree function. And we get a really simple and very elegant learning algorithm for AC0. But this is not a talk about AC0, it's a talk about QAC0. So let me tell you what QAC0 is, and then I'll tell you what we did with QAC0. So here's the quantum circuit model from my first to second slide. In analogy with AC0, we're going to assume that the depth is a constant. So think of 100 layers or so of gates. And we don't just allow for arbitrary gate sets. We have a specific, we only allow for CZ gates. However, we have no restriction on the width of a CZ gate. So to summarize, a QAC0 circuit is a constant depth circuit where you have arbitrary single qubit gates and CZ gates of unbounded width. Okay? And there's a slight catch, which I'm going to try to sweep under the rug as much as possible. There are some ancilla qubits as well, and this will come up, and I'll let you know when it comes up later. But for now, pretend that there's no ancillar qubits. Great. So why might you care about QAC0? Well, this is the simplest circuit model that captures non-local computation, right? You're not assuming that these CZ gates only act on 2 or 3 qubits. It's like they can act on many qubits. It's also believed to be a physically realistic model. And in some sense, this is also the class that you could hope to prove unconditional lower bounds for. So if you try proving unconditional lower bounds for any slightly bigger class, you would get breakthrough classical circuit lower bounds. So in some sense, this is what we're supposed to shoot for. So and just this model was introduced by Moore in 1999, and when he introduced this model, he asked, in analogy with the setting of AC0 and parity, he asked if polynomial size QAC0 circuits can compute the parity function. Okay, so this was asked in 1999, and it's been 25 years, and we've made very little progress on this question. So let me quickly summarize what we know about this problem. We know that if you've got a constant depth circuit with, I think, log n ancillar qubits, then you cannot compute parity. We know that if you've got a depth 2 circuit with any number of ancillars, with an arbitrary number of ancillars, then you cannot compute parity. And I think in 2021, Greg showed that if you've got a constant depth circuit with sublinear number of ancillars, sublinear size, sorry, then you get somewhat poor correlation. I think he showed that you mess up on a polynomial fraction of the input space. And what we show in this work is we show strong average case lower bounds. So the correlation is negligibly greater than half with parity, and we also reap a few more consequences. So if I had to show you what we prove, I'm just going to reuse my slide on the results for AC0 circuits. I'm going to scratch the title and replace it with our results on QAC0 circuits. So we show that QAC0 circuits are in some sense Fourier concentrated. You get correlation bounds for parity and more generally for high degree Boolean functions. And you get a quasi-polynomial sample learning algorithm for QAC0 circuits. Great. And for the rest of this talk, I'm just going to tell you what the Fourier spectrum of a QAC0 circuit even is. Boolean functions are computing, classical circuits are computing a Boolean function, but quantum circuits are computing a unitary. And a natural representation of a unitary is the Pauli expansion. We all have seen this in some form or the other, or we've certainly seen this. And this Pauli expansion has, a lot of recent work has shown that it does behave a little bit like the Fourier transform of a Boolean function. Like people have done similar kinds of analysis and trickery to get results for quantum circuits and unitary complexity as in the classical setting. And so if you remember LMN, Lineal Mansur and Nissan's bound, which said that AC0 circuits are approximated by low degree polynomials, a natural guess with this Pauli transform, this Pauli basis, is that QAC0 circuits are approximated by low degree Pauli nomials, right? What do I mean by the degree of a Pauli tensor? It just is the number of non-identity components of that tensor, okay? But this conjecture is false. It's false for a really silly reason. If you take the following depth 0 circuit, which just is the all z's tensor, it's got depth 0, it's got Pauli degree n, all components are non-identity. It does not have like a tail bound. It's a depth 0 circuit, but has high degree. But this is in some sense morally a degree 1 function, right? Like we're interested in QAC0 circuits which are computing Boolean functions like the parity function. And so we really are only interested in the output of a single qubit. And so in some sense, this should only be a degree 1 function. And the key insight of our work was to find some way to capture this intuition. So what we did is we decided to treat quantum circuits as channels. A channel is just a map complete the CPTP map from n qubits to L qubits, and we're going to treat quantum circuits as channels mapping n qubits to 1 qubit, so 1 target qubit. And we do it as follows. So you've got some input state, you've got some number of ancilla qubits. You just trace out all the other qubits but the target qubit. And we want to do Fourier analysis or some kind of Fourier analysis on this object. And it turns out we can do this, and the way to do this is to use the so-called Choi representation. So let me tell you what that is. The Choi representation is just a convenient encoding of a channel as a density matrix. So for now, just pretend there's no ancillas. I'll come back to ancillas in just a minute. So in order to tell you what the Choi representation is, you just pass a bell pair. You just take a bell pair and you act on the second register, second half of the bell pair using this unitary U. And then you trace out all but the target qubit of the second register. And the resulting object is a state on n+1 qubits. You've got a density matrix. And so you can write down its Pauli expansion, right? So our main theorem is that if you have an n+1 qubit Choi representation as follows, then you get the tail bound that Lineal, Mansour, and Nissan got in the classical setting for QAC0 circuits. And I'm not going to go over the proof. I think I'm almost out of time. But the idea is to do some kind of hybrid argument and kind of take care of it using the Fourier transform. Like, it allows you to control the distance in a clean way. And we also use light cones. Like, we haven't completely abandoned light cones. I said pretend that there's no ancillas. So let me tell you what happens when you do have these ancilla qubits. We treat them as inputs, and then we post-select on the output. And consequently, when you have A ancilla qubits, you have a 2 to the A blow up in this tail bound, which makes us unhappy. Okay? So as a consequence of this, this Fourier concentration bound, you get a circuit lower bound, you get a learning algorithm. The learning algorithm is similar to Lineal, Mansour, and Nissan's, but it's a little more complicated. It uses quasi-polynomially many samples, but the runtime is exponential. And so to summarize, we introduce this notion of a Pauli spectrum of a circuit and kind of mimic Lineal, Mansour, and Nissan. And there's a bunch of open directions. We conjecture that the spectral concentration bound we proved holds for polynomially many ancillas. It's natural to hope for these connections to pseudo-randomness and these other circuit complexity flavored questions. But I think I'm going to stop here.
Great.
Thanks.
Any questions? Please step up to the microphone.
Hi, that was a really good talk. Could you go back to the part where you talk about the ancillas just a little? Oh, right there. Yeah. Do you know if that A is like necessary? Is there an example that witnesses that, or is it possible to get rid of the dependency on the ancilla?
I think there's going to be some dependence on A. I forget what it. I think we worked out some kind of lower bound, but I don't remember it off the top of my head. But there's going to be some dependence on A. Yeah.
Okay.
Hi, thanks for the nice talk. If you just take your constant depth unitary and conjugate, say, a single qubit Z operator.
Sorry, could you?
Sorry?
I couldn't hear you. Sorry.
Oh, I'm sorry.
Yeah.
If you take your unitary and consider the Pauli expansion of U, Z, U dagger, where Z is a single qubit operator.
Yeah.
Does that have a similar?
It does.
property?
It does. That ends up being very similar to what we do.
I see.
Yeah. So if you look at the paper, there's like these tensor network diagrams, and I think Fermi-Ma made the same observation independently, but it ends up being very related to what we do. Yeah. It's essentially the same thing in disguise.
Thanks.
Yeah.
Thanks for the talk. So could you highlight some differences between this kind of an expansion and the classical Fourier expansion? For example, like I think this is not unique, right?
It is unique. The Pauli expansion is unique.
No, the Choi representation.
Oh, the Choi representation, it is not unique. That is true. That's a good
So,
point.
like, could you highlight certain differences, like apart from the uniqueness?
Apart from the uniqueness, I can highlight similarities for you, but I don't have differences besides
I
the
see.
uniqueness. Yeah.
Any more questions? Last chance. Okay, if not, let's thank the speaker again.